Okay, so on the pause weakening of the AMO, Atlantic Meridian Overturning Circulation. So, so Atlantic Meridian Overturning Circulation here, AOML, we just call it AMO. So I'm going to just call it AMO or MOC, something like that. So first of all, when you look at this title, you'll see you will have a lot of questions, a layer of questions. First of all, weakening of the AMO. You know, I don't think there is any weakening or any really clear evidence that it's weakening. So, you know, that is the question. And then pause weakening. So, like, there has to be weakening first to have it pause. So, you know, I'm sure you have a lot of questions about this title. And yeah, I'm going to explain the whole why I selected this title. And then my name is there. And then my collaborators are there too. Okay, so okay, I didn't practice, so let me see what I have to say. Okay, so this here, you can see my cursor, right? So this is the I got it from Menery et al. 2020. So this is MOC at 35° north from CMIP 5 in blue, and then CMIP 6 from red. So you can see that it gradually increased from pre-industrial period, then it increased pretty intensely over here from about 1940, and then around like mid 1980s, like 85 or so, it started to decrease. And then you can see this similar patterns in CMIP 5. And then the next one in the middle is a DAMIP. That's, I think, detection and attribution model intercomparison project. So this project is basically a handful of a small group of CMIP 6 models. These models are forced with a single agent. For instance, like aerosol only, ozone only, and then greenhouse gas only, and natural only. Natural here is basically we're talking about volcanic eruption. So if you look into it, so you see that the aerosol is trying to increase the MOC up to like 90s, then it's slowly decreasing because aerosol, anthropogenic aerosol is decreasing in the northern hemisphere, and then greenhouse gas is trying to slow it down. So they kind of cancel each other, but working together around from 85 to 2014, which is the end of the historical period, is going down about like a 2.3 Spurger going down. So it's not a huge, but if we compare that reduction to the observed mean value at 26.5° north, we're talking about like a 40% decrease during this 30-year period. And then if you look into CMIP 6 projection beyond 2005 to all the way to 2100, that decreasing rate is about 13 to 17. I'm sorry, that's about 6 to 8 Spurger during this 85-year period. So that accounts for like 13 to 70% decrease per 30 years if we translate it to 30 years. So this decreasing that has happened during this period is about the same. The rate, the slope is about the same as what we expect to happen in the future in the rest of the 21st century. So it's like when you think about AMO weakening, we think about that's something that's going to happen in 20 years or 50 years from now. But in fact, what models suggesting is it already happened. It started around 85. And then in a rate that is like constant. That's exactly the same slope that's going to happen in the future. So it's happening, and then it has been like 40 years. So 40 years of externally forced weakening of the MOC has happened. So 40 years is a long time. Yes. So let's see what happened with the direct observation. So you can focus on this, the second one. This is total MOC. You can see that starting from 2000. 2004, you see a big decrease, slow decrease, and then it decreased down to very minimum value around 2009 and 2010. So there was a big decrease. So there's a very robust weakening during this period. But after that, it recovers, slowly recovers, and it peaks around 2018, then weaken again to like 2021. But if you take a look at the interdecadal changes, so what I'm saying is the first 10-year average, 2005 to 2014, then compare with the rest of the period, which is 2015 to 2021, 7-year period, the change is very slow. So at interdecadal time scale, it's very small weakening, low weakening. But of course, so I have to make a distinction between interdecadal changes and decadal changes. So what happened here, 2005 to, let's say, 2014, so this 10-year period, there's a robust weakening. That is a decadal trend. But this, my talk is about interdecadal, really long-term changes, like that. So anyway, for the decadal trend, for this first 10 year, it's like a full Sverdrup per decade. So it's a huge. So okay, let's talk about that decadal trend first a little bit more. So this is a very nice study by Latiferro, published in 2019. What they did was that they actually look into their model, PL climate model, along with the other simplified model, but they're looking to this pre-industrial periods. That's where there is no external forcing. So no global warming, aerosol, nothing. It's just all natural variability. So they selected this 50 model for the 150-year period for each of the model. They look into the decadal trend of any period in this pre-industrial period. They look into this probability distributed function of it. So you see that sometimes, most of the time the trend is 0 with just natural variability, but sometimes it can go up to like almost close to 8 Sverdrup trend. So you can have your MOC increase by 8 Sverdrup within 10 years, or decrease by 8 Sverdrup within 10 years. That's, some model has very low variability, but some model has huge internal variability. So that's what's happening. So what they argue was that, okay, this appears to be very, very strong trend, but you cannot really distinguish from natural variability if you look in this way, because your model, without any extra forcing, you can have it like this. This is a rapid, so it's a full forcible drop reduction in 10 years. Your model, internal variability, can actually make it up to like 8 Sverdrup. So this could be natural variability. So that was the conclusion. We cannot say that this is global warming, external forcing, or natural variability. So Roberts et al. In 2014 pretty much did the same thing, very similar types of analysis, and made the same conclusion. But at the end, they're saying, okay, detecting the influence of external forcing requires more than 10 years of continuous observation to be able to detect. That was their conclusion. But there's a problem with this approach, because if you think about this anthropogenic weakening of the AMO, we're talking about very, very tiny. So do you remember the value that I showed you? 2.3 Sverdrup within 30-year period. So that means within 10 years, we're talking about 1 Sverdrup or less decrease. So if we actually put it in this graphic PDF, it'll be somewhere there. It'll be somewhere there. And then let's say we're measuring the MOC until 10 more years. We have been measuring 20 years. Let's say we're doing it for 10 more years, 20 more years, 30 more years. Let's say we're in like the middle of 2050. So we have like a 50 years of observations. And then if we do it this way, if we analyze it this way, we'll never be able to say this is external forcing or natural variability, because I will show you one example that some model ensemble can actually produce more than 5 Sverdrup increase or decrease within 50-year period. I will show you one example of it. So you will never be able to distinguish that if you use this approach. So I use somewhat very different approach. So I'm going to talk about it later. Okay. So main goal of my talk is to attribute the historical interdecadal, not decadal. Interdecadal means 1 decade average to the next decade average. So it's a long-term interdecadal aim of evolution to the anthropogenic and natural signal. Okay, so that is. And then I have a couple of specific research questions. First thing is, was there a long-term weakening due to human activity prior to our observation? That's one question. Next question is, if that's the case, what caused very small change or in a pause? So I call it pause weakening of the AMOC from first 10-year period to the next 10-year period. Not 10, 7 years so far. Then I'm gonna address another question, but I don't think I have the time for that. So I'm not going into that. That's about what's going to happen in the next 10 years. Yeah. Okay. So this is a little boring part. So this is the data method models part. It's boring parts, but it's important. So I use a rapid MoCA Western boundary time series to get the total MOC from 2005 to 2021. So that's the total MOC. And then I use a CSM2 model-based surface force ocean sea ice model. So this is forced with the JRA 55 reanalysis atmospheric fluxes, the force model from 1958 to 2018. So that the AMOC derived from this ocean model will be used as a proxy for total MOC. So this will be combined with total MOC from the rapid MoCA array. And then I'm using CSM2 based large ensemble simulation. This will be used to represent externally forced MOC components. So I'm sorry, the ensemble average of this simulation will be used as an externally forced MOC component. So it has 80 ensemble. It covers a historical period from 1850 to 2014. And then future period of a medium to high emission scenario, SSP 370 scenario, from 2015 to 2100. So it has 80 ensemble. This simulation is really interesting because they actually have 4 different set of the initial condition coming from long-term pre-industrial simulation. So they pick, it's a really MOC specific. So they have a 20 model run at the initial condition of 1850 with a very high level of MOC. So no forcing, just internal productivity, very high level. So they have a 20 ensemble. So that with a slightly different condition, they run the 20 cases. They have another set of 20 that is MOC decreasing phase. They did that. And then they have another 20 set that is at the minimum phase of the MOC, 20. And then they have another one that is upward phasing MOC. So they have 80 different collection of this simulation forced with the same historical forcing and future scenario, but with a different initial condition. So this is a really MOC specific experiment. Okay. And then I have, finally, I have the residual MOC components. So it's basically the difference between the total. Total is from the observation and then surface force ocean model. That is total. And then take the difference between the total and the externally forced MOC. So that will be the residual components. And that should represent, natural MOC components, providing that the ocean model and climate model represent realistic level of the MOC. That's a big if. Yes, it's bigger. Yeah. So I know what you're thinking. So I know what you're thinking. How can we trust it? Yeah, we'll get to there. We'll get there. We'll get there. So, so before we do the analysis, we need to do some adjustment, because if you look into this MOC plot from the ocean model, it's pretty weak compared to the rapid MOCA at 26.5. And then if you look into climate model, large ensemble one, this ensemble average is pretty high compared to the observation. So I had to do some adjustment to be able to put all time series into the same picture. So I did some adjustments here, a very reasonable adjustment. I did it. So this is what you see at the bottom. So where's my cursor? Yeah. So green here shows the ensemble average of the climate model. So that should represent external forcing components. And then this blue line is from the surface ocean model. So this total components. And then we have this rapid MOCA array, time series, the total. And then this envelope here is basically 2 sigma of the internal variability within those 1880 ensemble simulation. But it turns out that this internal variability in this model is is really small. So what I did was that I compared the internal variability within of the rapid MOCA array, that compared that with the ensemble spread of this model. It turns out that it's about 2 times smaller in the model. So I just multiplied 2. That's what you see. So basically, this line, orange line, shows that all your ensembles are within this. About 95% of the ensemble members are within this line. So this is kind of a upper and lower cap of this distribution. And then this gray line is just an example to show you. I'm not going to use it for the later analysis, just to give you an idea that how each ensemble member look like. So if you, for instance, if you take a look at this one actually start from pretty low, and within like a 50-year period, it increased by like a 5 squadron. This is nothing to do with the external forcing, but it can happen. I mean, it could be, but the external forcing is so small at this point, but it could, because of the internal variability, it could really create a huge trend this year. So I talked about it a little bit. So okay, so that's it, and then let's move on. So from now it's the result, main result. So this is the main result. So this is MOC at 26.5 degree north. So this is same as this plot here, but this is interdecadal thing. So I just average all this thing for each decade. For instance, if it is 1970 here, this is basically 1965 to 1974 average. If it is 2000, this is 1995 to 2004. This 10-year average. So it's a long-term average. It's a decadally averaged the plot. So you can see that. So this is the blue is the total, and then you can see the magenta here. This is the total, but from the rapid MOCA array, and then the green is the external force one. And then the orange is the difference. So it's a residual. It's supposed to be natural variability. Okay, so I'll get back to that. But this plot is a bit problematic because it's not. I don't think it's a big issue, but it's not very objective. The reason is because this rapid MOCA, ocean model, climate model, they all have a different need. So I did some adjustment, right? So I pull it down, some of that, I pull it down the time series, pull it up so that I can put it at the same, I can compare it. But because of that, in other words, the mean of the MOC in 3 different products are a little different. So if I use slightly different adjustment, this whole thing will change, like this may go down, then this will go up like that. So it's not really that objective. So what I did, but what I'm going to show you in the next plot is basically, I'm going to show you the rate of change. So I'm going to show you in the next slide is the difference between previous decay to the next decay. So I'm going to show you, okay, so the total was here, it was increased this much, right? So the rate of change will be positive here, right? So it's just you know, the difference between the two. And here to here is almost the same, right? This green. So the increase will be very small, something like that. So if we do that, then this constant value that I used differently for different product will be irrelevant, because this constant, if you do time derivative of the constant, is gone. So that doesn't really come into the picture. So if I do that, that plot looks like
what was the error bar on the green? What are the error bars?
Oh, thank you. Yeah, I forgot about that. So this is a 2 sigma thing. Basically show that each of the this ensemble member of this large ensemble simulation, this is like the amplitude of internal variability that you would expect. So yeah, that's a good point. I'll come back to that. Yeah, I'll come back to that also. So I'm going to use this plot, but I'm going to rely more on this plot. This one is not very intuitive compared to this, but you know, you'll get used to it, hopefully. Yeah, it took me a long time to get used to it, honestly. Yeah, this is not easy. But look, so here you see this negative value. That means you have the total MOC, you have total MOC previous decay, next decay is decreasing. That's what it means. So it's a decreasing. If it is positive, it means the residual component is increasing from here to here. That's what it means. But yeah, don't worry about it too much. Yeah, we'll get back to that. Okay, so 25 minutes. Okay, so now I'm going to describe this plot. So take a look at the first the upper plot. Show you that you see that these total components are blue, and then externally forced component, it seems to have a somewhat similar interdecadal swing. For instance, like they are increasing from, both of them are increasing from 60 to like 1990, right? Both components increasing, and then there's a decreasing from this 1990 to 2020. Where is my cursor? 2020. Which means, so it seems like this interdecadal variation of AMOG is somehow partly, at least partly, forced by the external forcing. It looks like it. But this internal variability, like Rick was telling us about, is really huge here. The internal variability is so huge. So this the internal variability must be playing an important role here. So, for instance, this total increase from 60 to 90 is about like this, and then that is much larger than this increase in the green components here, external components. So let's take a look at the lower panel now.
So, Seki, could you remind us again what the residual is? That's the internal,
Supposed to be,
natural.
supposed to be, yes. Supposed to be, yes. Thank you. So here, if for the first, oh, where's my cursor? Yeah, here. So this is a rate of increase. So the total increase here, and then you see that it's largely due to the external forcing. The increase is comparable to it. So what happened during the 60 to 70, 70 to 80, this increase is due to the external forcing, particularly aerosol forcing. But take a look at what happened between 1980 to 1990. This is, oh, where's my cursor? The total increase is nothing to do with the external forcing. It's 100% has to do with the internal variability. if this is correct. Yeah. So, so by and all, this internal variability seems to be the much more important during this period compared to the external forcing. There was also, oh, I should, no, I talked too much here. It's supposed to be next slide. Okay. I already talked about it here. So just focusing on this first time period, 60 to 80. Yeah. Yeah. So yeah. So we can conclude that the external forcing from 60 to 90 is mostly it's not the primary driver of the MOC increase during this time. It was mainly internal variability that increased the MOC from 80 to 90. And that was a big thing. And then, of course, more important thing is more recent period, the weakening period. Let's take a look. So this decrease is about from here to here. Decrease is small, but the external weakening is much greater. Yeah. And then you can see that this natural variability is trying to compensate this. So it is trying to slow down the weakening. But it actually weakened, right? So our conclusion is that we can conclude that external forcing is the sole driver of the MOC slowing down from 1990 to 2020. That's a big conclusion. It was an anthropogenic forcing. I know you don't believe it, but we'll discuss that. We'll show you more evidence later on. But what it showed is that basically it was anthropogenic forcing that drove the weakening, and natural variability was trying to resist so that it slowed down the weakening. That's what it says. And then, all right. So, and then this is a bit of a disagreement with the conventional idea that, so this modeling community, especially surface force ocean modeling community, thinks that this weakening of the MOC from like in 1990 to now is due to because of NAO was very strongly positive in 1990 and it crashed later on. And most of the people think that this is due to the natural variability, the weakening due to natural variability. So this is disagreement with that idea. And I'll tell you, I published one paper last year. I said the same thing there. It was due to NAO, but that is not what this analysis is saying. So that's where things get really interesting. Yeah, that's what I said. Okay, and then so if you look into just focusing on the recent periods where we have observations, so that we are just for the total MOC, we're going to use just the rapid MOCA. We're not using ocean model. Let's just focusing on this period, and then let's just take a look at what happened during this slope here. What happened is 2010 to 2020. Oops. By the way, when I say 2010, I'm not saying 2010, that year itself, that the decadal period centered at 2010. 2020 means decadal period centered at 2020. That's yeah. Just want to be careful about it. So you see that if you take a look at it, what happened during this period of the direct observation, the mitigating effect of natural variability becomes so large that it really almost completely compensates for the anthropogenic weakening of the MOC. So the total MOC decreases almost nothing. And then we learned about a month ago from seminar from Dennis that this will get even smaller very soon. Yeah. So look like it's a pulse weakening of the MOC. So it was weakening because of anthropogenic forcing, but during the recent period, it paused. That's That's what my title of my talk is about. So, so that's main part of my talk. That's the introduction of my talk. The real part of my talk is about why this natural variability has to increase. Is there a reason to believe it? That is my main part of my talk, which I'm going to start now. So the more important question, does the interdecadal variation of the residual component represent natural variability? It should be, or can it be just an artifact of model errors in the climate model and ocean model? Probably, right? So in order to answer that question, we can ask a more specific question. That is the interdecadal variation of the residual MOC component physically consistent response to its main driver that is known to us, that is interdecadal NAO variability? Does it make any sense? So let's look into this. Let's explore this question. So here, I'm sorry, this plot also a little funky. So I'm sorry about it. So okay, so yeah, here, this bar here, the left side, is basically decadally averaged NAO. So 60, 70, 80, 90 altogether. And then the right side, the orange line, is basically residual MOC that I show you from model as well. So the NAO and residual MOC looks very different. Looks like it's a random thing. If you do correlation, probably zero. But we got to look at it more carefully. What's really happening here? So so let's take a look at the part that makes sense. For instance, here, NAO was from 80 to 90. NAO was almost neutral. And it jumped into very strong positive NAO. Again, this is a 10-year average. This is not just 1 year to 1 year. This is a 10-year average, nothing, and then very large positive NAO. And probably as a result of that, the MOC was the residual MOC was pretty weak. Then it jumped pretty big. So this jump was pretty big. So that seems to make sense. And then let's take a look at this part where we had an almost neutral NAO. It become pretty strong positive NAO. And then it jumped from residual MOC was jumped from here to here. So that seems to kind of make sense. But what about other periods? This is consistent with the previous modeling studies and all that, but there are parts that doesn't make much sense. For instance, here. So NAO was pretty negative, so it's warming in this polar region, and then that really disappeared. So we expect this reduced MOC to recover, but it didn't recover, and it got even smaller, a little bit, tiny, but it just remains the same. So what's going on? Number two, here it was very strong NAO in 1990, turned into almost nothing. And then residual MOC actually didn't crash. It just increased a little bit. So this two part doesn't make much sense. So the question that I ask myself, is there any reason why this relationship is physically relevant, consistent? So before I show you the result, my God, yeah, I gotta rush. Okay, so let me do some just thought experiments where, let's say you have, this is a subpolar region, and this is subtropical Atlantic. Let's say you have for 10 years, you have a positive NAO, so that there's a strong cooling in the subpolar region that will cool this subpolar region very cold. In response to it, MOC should increase the heat transport, so on and so forth. But in the later 10 years, if same amplitude, strong negative NAO comes, hitting it, that cooling should almost disappear. so that the anomalous MOC should disappear, right? So that's pretty logical, right? But this is not our case. Our case is this. So we had a very positive, strong NAO and a cooling the subpolar region. But in the later 10 years, there's neutral NAO. Neutral NAO means no flux, no anomalous flux. So what happened to heat that was like really cooled down in the subpolar region is still there. We didn't anticipate it. So that should actually create a strong pressure gradient, and eventually that will lead to increased MOC. So MOC should stay increased. See? So switching from positive to neutral NAO should not dissipate the NAO-induced ocean heat content anomaly. So of course, the MOC is increased, so that would actually warm it up and dissipate everything, but that may take a long time. And also, it takes time to spin up the MOC too. So those kind of things. So that's the basic idea. And then, based on that idea, what we can do is we can do the time integral of NAO and then compare that instead of NAO, time integral of NAO, which should mimic the heat content in the subpolar region, and compare that with the residual MOC. If we do that, this is annual mean. I use the annual mean NAO, but if we use a winter NAO index, it kind of looks pretty good. This purple is a time integral NAO, and then this is the orange is the residual MOC. They kind of looks kind of similar kind of idea. So you see what I'm talking about, the idea behind it. Okay, so this is the main result. So in order to test this hypothesis, I did some composite analysis. So there, I have 80 model ensemble, a huge number of ensemble. I remove the ensemble mean, so I only have a natural variability in it. So I select those composite of these combinations where model was forced with a negative NAO, positive negative NAO for 10 years, and then neutral NAO for next 10 years. I make those composite. I found about 200 cases like that, average them all, made a plot. That's case one. Case two, it start with a neutral NAO, then it turned into positive NAO in the later 10 years. Case two. Case three, you have a positive NAO for 10 years, then neutral NAO for next 10 years. So I make this composite of 3 cases, and let's see what happens. This is case one. So you start with a negative NAO for 10 years, so it should decrease the MOC. So that makes sense. But let's see what happens when we just turn off the NAO and it becomes neutral NAO. And take a look at what happened in 26.5. It actually increased a little bit because this blue color here is now here. It not only stays strong, it actually increased. And then here from neutral to positive, of course, increases. That's what he expected. Take a look at the positive NAO for 10 years, then kill it, and then neutral NAO, and then it increased again here. So what's going on? But of course, I mean, if you look into subpolar regions, let's say north of 45, this is reduced. This is weakness here. So this seems to be a different physics here. It's probably like the convection itself, driving forcing itself directly change the MOC there. So it is no delay there in the subpolar region. But subtropical region, it stays there. Osmo is sleeping? No? Okay, I'll finish in 5 minutes. Okay, so that's it. And then it's not just one model. Take a look at this paper from Tim et al. Published this year, 2024, and they did it's not a composite. They did an actual idealized experiment. They put the positive NAO for 10 years. They just kill it, turn it off, and see what happened in next 10 years, and next 20 years, and next 30 years. And look at this. So MOC stays here, stays pretty strong. And then this is a different model. This is, I think, a UK model. It also stays strong. And then there's another version of another model. I don't know where, but it stays strong. So it's not just model. This model, other models also shows the same thing. So this is a summary plot. So what happened was that from previous decade to this decade, there was increase in the MOC because of the appearance of the. I'm sorry. This is by the residual MOC. So increase in NAO positive. So it happened. It happened. Same thing happened again. 80 to 90. In between, we have a positive, strong positive, turn into almost a neutral or like that. But it didn't increase. It didn't decrease. It didn't die out. Oh, by the way, this is not MOC. This is a change. This is rate of change. So this is an increase. This is also increase. Oh, by the way, I'm sorry. What I'm showing you here is actually the time changes here from here to here. So increase here or decrease here. That's what it's saying. So no big changes here. So that really checks out. So this is it. This is it. I'm done. So here's a summary. So let's see what happened. So I'm showing you from 90 to 80 to 90. There was a huge increase in the residual components here. Oh, where's my person? Because of the NAO appearance of positive NAO. External forcing, nothing. And total increase due to internal volatility. In between, what happened? The NAO turned into neutral, so no big changes, stay the same. Here, external components keeps on weakening, and then total weakening because there is no big changes here in the residual components. So weakening, and then here during the recent 20-year period, there was a strong increase in the residual components. And there was a fighting against the anthropogenic weakening. So combining it, nothing happened. Pause in the weakening of the AMO. That's it. That's it. And I have so many other slides. Like this is just half of my presentation, but I think it's yeah. I'll just take a message there, all there, and then I have questions and limitations and more limitation, future work, other things to consider, whatever, so many things. But I think I will just stop there. Thank you.